ask me before we continue. Yes, you had a question at the end, yeah.
So normally in the topological A model, you compute the open-string spectrum between special Lagrangian branes by looking at the Floor homology groups. Does this match with that at all? I mean, a different way to think about it is you can have a few special Lagrangian submanifolds that you wrap these 6 branes on, and then you can fix the intersections via prescribed angles locally.
Right.
So then you get a supersymmetric spectrum. But
well, yeah, if they are both special Lagrangians with respect to the same phase or with the same set of supersymmetries, there are additional conditions. Each of them can be special Lagrangian, but a condition, in complex manifolds with Kähler form would be that the holomorphic 3 form, the Kähler form on special Lagrangian has to be 0. That's Lagrangian, but then to be special, right, it has to be imaginary part of holomorphic 3 form with respect to some phase, okay, has to be also 0 when restricted to special Lagrangian. Now, if you have special Lagrangians that are special with respect to different phases, okay, then you can have them, they are not mutually supersymmetric necessarily. Okay,
so if you pick two that are mutually supersymmetric,
yeah,
and you fix their angles of intersection,
mm-hmm.
you get a supersymmetric spectrum.
You don't have to fix them anymore. It's automatic. Because if you fix them with respect to the same phase, okay, then it turns out that locally, indeed, the intersections locally have the property that the sum over those guys is 0 modulus 2 pi. That's, I chose particular convention when I described it locally, right, with the choice of 2 angles, positive and 1 negative. Anyway, okay, now.
You can imagine deforming one of the special Lagrangians that fixes the angles of intersection, but so that it's no longer a special Lagrangian.
Mm-hmm.
You break supersymmetry.
Right.
So some of the global properties looks like you can't capture locally.
I mean, the way you can technically do that in principle, okay, you choose a complex structure of the 6-dimensional manifold to be of certain type so that ensures that special Lagrangians are mutually special, right? And that ensures supersymmetric spectrum. Now you can think of deforming complex structure of this manifold. Okay? What this would do, it would start deforming the cycles relative to each other. Okay. So they need not be, yeah, maybe we can discuss that later, okay, because I'm going very slow. Yeah, thank you, Tom, because I'm really, But we can discuss it privately, okay? The way, in flat background is, of course, rather easy to do, but in general, you can deform these angles by changing complex structure and not having them special Lagrangians anymore. As a consequence is that, locally on each brane, even if it by itself, right, it's Lagrangian, you could have supersymmetric spectrum locally, but at intersections it's broken. So the whole spectrum of the theory is non-supersymmetric, and locally the way I was encoding that is by writing for you actually in principle exact conformal field theory and mass of the lowest lying state. Okay, so let me maybe go on, and we should privately discuss. I'd love to. Okay, still any other questions? Okay, so we went through quite detailed analysis arguing about the spectrum at intersection of each branes, and the third thing that we also obtained yesterday is that actually the number of intersections was equal to the intersection number of the corresponding 3 cycles. So basically, we are at this level, at least locally equipped to address the spectrum that could become, that could be in this framework, that could have features of the standard model. Okay? So in particular, let me just be a bit more concrete. One option would be to associate with each cycle that a set of branes wraps a particular gate symmetry of the standard model. So one way would be to look at embedding now in this internal space. So let's just focus on this part, that we choose a 3-cycle with 3 brane, which will give us U3 symmetry, which we would associate with the color. And then with another one, we would associate that with U2 symmetry of the electroweak symmetry. And we would engineer intersections of those 2 sets of cycles to be such that their number would be 3. Okay, so that would be an engineering prescription in the internal space. For example, if intersection of U3 and U2 branes is chosen to be, let me do it like this, okay, to be equal to 3. That will give us at each intersection multiplets in bifundamental representation that would act as 3 copies of left-handed quarks, which would be in the representation 3, 2 bar. Okay. Now, we still have to generate, in principle, of course, the hypercharge. So typically, the way one does that is implementing additional branes. In some cases, those could be U2 right symmetric branes, if we want to derive standard model from left-right symmetric constructions, or we could add additional set of branes, more than one. So let me call that U1A, and let's say another one, right? That would be, so you see that's getting very busy already. So another one, U1B, and we would choose a combination of U1A and U1B in such a way that would correspond to the hypercharge. So some combination of U1A, so let me call it alpha plus beta, U1B will be defined as a hypercharge properly. That could then, in principle, you see at each intersection, for example, when we would be intersecting U2 brane, so U2 brane with one of these U1s, we would get left-handed leptons, for example. Left-handed leptons would sort of appear from intersection, say, of U2 brane. So there would be singlets under U3, there would be doublets under U2, and then they could have some additional charge, say, under U1A, additional one. Also, Higgs doublets could appear from such intersections. And so that would be singlets, doublets, and maybe another set of charges under extra U1s in such a combination that they would have the right hypercharge. As far as right-handed quarks go, we would intersect U3 brane with U1A or U1B, additional brane. So that would give us, for example, right-handed quarks and up or down. So they would be, let's say, 3 bar, singlets under U2, and then they would have some specific charge under, so they would intersect between U3 brane and U1A and U1B brane. So let me not put exact numbers because that crucially depends in a way in which we construct this hypercharge as a combination of U1A and U1B, and similarly for 3 bars. So that's a framework in which we actually construct standard model, okay, by taking stacks of branes, okay, building them basically from U3, U2 brane, and the rest to ensure the proper U1 hypercharge. Okay. Okay. Yes.
From this, can we get matter which is non-trivially charged in the all three gauge groups?
That is not charged.
Non-trivially charged under all the gauge groups.
So as we saw up to now is we focus on intersections and quantized string theory locally on intersection. So we are pretty much forced to deal with the massless spectrum of chiral fermions only at intersections. And so they are necessarily in bifundament representation. So this is, a certain obstruction in this perturbative picture of type 2A theory to construct higher type of representations. Okay? Yes? Yeah.
Understood why one doesn't consider the possibility that some of the U1s in the U's versus SU's don't come into the hypercharge.
They actually, I was sloppy, but Jim could correct me. There could be this as well. U1 of color. So let me call them C plus D U1 of left-handed symmetry. Actually, typically, we have to employ all of them. Okay, you're right. Okay, so since Jim knows that by heart because he has actually analyzed these quivers in glorious details, and under which condition we can actually obtain hypercharge that has the right quantum numbers. Okay, there is additional issue to which I'm coming to that actually those U1s typically are massive. So we have to be very careful the way we construct combination of these U1s, that at the end we would have one combination corresponding to hypercharge and being massless. So those are issues that to which I want to turn because they are related actually to important issues of anomalies and global consistencies of these models. Yes?
So why don't we get, for example, like a 3-bar, 2? I mean,
Right.
Projecting out one of the orders.
Very good, okay? So the issue here is this issue, whether it's coming in this combination, whether the representation of chiral matter that we obtain is in this representation or the conjugate representation depends on the sign of intersections. Okay? So what I'm trying to say is this intersection number, as you know, it's an integer number, but it can come with different signs because it depends in which direction cycles are oriented. Okay? So we choose, okay, for physical states, so this is a convention, okay? A convention by which I'm going to, for example, if this intersection is positive, okay? So to be compatible with our review, actually, I have to, now it's going to be a gain. We choose these representations, okay, of fields to be in bar. So it's really this choice with the convention there. So if we want to have, and so we associate it with left-handed fermions, for example, representation, okay, that is bar and fundamental if intersection number is positive. I mean, we choose this convention consistently once, okay? So then for all the other, for example, if this is my convention by which I'm determining the number of left-handed fermions in the theory, okay, then all the others are fixed. Okay. For example, for example, now with this convention, we see that U3 brane, intersection of U3 brane, so let me call it U3 brane, and U2 brane has to be -3 in this convention to have 3 copies of fundamental, anti-fundamental. Okay? Now, for example, to have right-handed quarks that would come in 3 bar, my notation is off. Okay, so this is U3, U2. Okay, this is U3, U2. And so to get bars, okay, I have to make sure that U3 brane intersects with, let's say, additional UA or UB brane in such a way that this intersection is positive. Say like this. because that will ensure that then the actual excess of chiral matter comes in bar representation under U3, and then it's singlet under U2, and then it has a specific charge -1, say, under U1A. So there are really 3 bars in the sense in which I want to have them as right-handed.
There's a proof that you can always do that?
Sorry?
There is a proof that the convention always does that?
Yes. Yeah. The point is that I have to engineer these intersections with correct signs, right? But that it's consistent convention by which it's rigorously shown. The thing is that forces me now to stick to the intersection convention, right? And so if one is positive to give me left-handed quarks, then between U3 brane and some extra brane to get right-handed ones, I need the opposite intersection number to get the right 3 bars. Okay, yeah? So this is what Tom actually erased. So here if I have, so U color, if hypercharge has to have contributions, okay? Actually also from U3, right, to the total value, so that, because left-handed quarks are charged under U3. That basically fixes this coefficient, okay? So that was the important thing that actually all of them contribute, okay? But there's more to the story. I have to ensure that the surviving U1 is strictly massless, okay, which will bring me to the next point. So in principle, you see, we have an engineering prescription by which at least as local constructions, local in the sense that I'm not worrying about global charges, okay? I can determine, particular multi-stack examples of branes wrapping cycles by which I would get the spectrum that looks like standard model spectrum. Okay? But you see, this is not enough to have completely consistent constructions. Okay? This is just, even at the level of spectrum, because we have to keep in mind that when we are in this compact space, okay, there is a D-brane charge associated with all the cycles. And we cannot let the total D-brane charge escape compact space. Okay? So to have really consistent constructions, I have to make sure that I have the total charge associated with all those D-branes to add up to 0 in internal space. And that's a very important consistency condition that goes under the name of Ramon-Ramon charge cancellation. And actually was observed doing the one-loop calculations in this framework and making sure that at the one-loop level we get finite answers. Okay? So let me turn before, so in principle, you see here we are, idea is sort of there in principle, but it's not all. It's not all. We have to make sure that whatever model we construct, we have to make it globally consistent, because actually those branes do live on internal space, and we should not allow the total D-brane charge to escape the internal space. Okay? So one way of deriving this global consistency condition, instead of going to one-loop calculation, is going back to an effective theory description by which we describe D-brane actions. So maybe I should, these things are now sitting, and so let's talk about global conditions. So one way of getting an idea about how to derive this condition that the total charge associated with the branes in internal space should add up to 0 would be to look at effective action that we get. First in 10-dimensional theory. Okay? So in particular, what we have, I already wrote down, with each brane there was associated Born-Infeld action, and there were also Chern-Simons terms, the whole Wezumino action. Okay? So let me remind you this, because this Wezumino action is the key one in the context of anomaly cancellation. So Wezumino action was of the structure for the P brane in 10 dimensions was described in terms of the forums in type 2A odd forums wedged with the Chern class associated with the gauge fields that live on this brane. So formally written, I mean just schematically in terms of gauge fields living on a brane. And then there was also associated things with the curvature induced on the branes, and is described in terms of polynomial of curvature that fall into Pontryagin classes, or just formally it's in terms of the so-called roof genus, written in terms of roof genus. Anyway, the point that I want to focus in, the Wezumino action part, and that's all integrated over particular P branes. So let's focus now, let's be concrete. Since we are dealing only with the 6 branes, this would be now integral over the word volume of the 6th brane, which splits into the Minkowski space word volume and the particular cycle wrapped by particular brane. Okay, so this is 3 cycle in internal space, right? Times that, this is the whole word volume of particularly the 6th brane, and then of course we have to sum over all of them. So specifically, let me just focus on the first part. What the key thing here is that actually the D-branes through this Wezumino action source 7-form potential, because this is 7-dimensional word volume. So the leading term is the 7-form potential. Okay, so when we actually wrap n branes, they source n times this amount of the 7-form potential, and then we sum over all of them. Okay, so that's a part that enters the effective action. Okay. Coming from Wezumino action. But of course, we also have the whole closed sector of the theory, okay, type 2A theory, which would have ordinary kinetic energy for this 7-form fields, 7-form field strengths. And so in the form notation, if the field strength is 8-form, obtain as D of 7-form. We have from supergravity part also kinetic energy. So the whole action associated with, so the part effective action that involves C7s, okay, Ramon-Ramon gauge potentials of the 7 forms will include schematically the term that will be associated with the kinetic energy of those field strengths, and then the term that I just wrote here. So I won't rewrite it again. But these are basically the terms in the effective action. This comes from the closed string sector, and this comes from the Wezumino action of the D-brane. And it's actually equation of motion for this 7-form potential that we have to satisfy. So whatever source, with this term that sources the 7 brane, the equation of motion for field strength gets modified. Okay. And the equation of motion. So in particular, let me just be a little bit more specific, because this integral here goes over the whole 4-dimensional space. So this is the whole R3, and then the whole internal 6-dimensional space, and then Wezumino action goes only over the word volume of the D6 branes. So the particular, using equations of motion here for D7, we get from the first part that actually D of the dual of H8 is now related to the part here, which we can write. You see, this was the part, this part goes over the whole word volume. Over the whole internal space, the integral. Here, the integral goes only across the word volume of the brane. Okay? So to actually replace this part with the same form, integral over the whole M6, so doing it over the whole M6, the way I'm going to fix that is by inserting 3 forums that are Poincare dual to those cycles. So thinking of introducing delta functions, okay, which are localized exactly on the location of this 3 cycles. So those would be 3 forums Poincare dual to those cycles that I'm just going to denote with delta function of that type. Okay, so think of it, it's a bump forum, that 3 form, but it becomes localized precisely in internal space on the 3 cycle. Well, it is a 3 forum actually. It's a 3 forum, and that's now the intro over the whole 10-dimensional space, right? I'm sort of allowing that, so I'm inserting the missing part to replace that with a full 10-dimensional integral. Okay, so then equation of motion, the right-hand side then basically becomes number of branes, and there is a tension, which here is also 1 over kappa square, but with units I won't be too careful. So this is so the right-hand side basically involves the number of branes, and then we have actually now the equation of motion pulls this out here, and the rest that we are left with as a local equation is NA times this bump 3 forums localized on each brane. Okay. So basically what it tells us that this equation of motion, when that's this is an exact forum on the left-hand side. So if I say d of that, this becomes 0, okay, which basically forces us, by introducing through Gauss's law, that integral of the of dual of H. So if I write dual of H8 as dH2 as a 2 form, and then use Stokes' theorem, dH2 now really, because it lives only in the internal space, over M is the same as H2 on the boundary of internal space, okay? Which, but this is through Stokes' theorem, tells us that this should be on the right-hand side basically related to the total charge associated with living in internal space, and we want this to be 0. Okay, so yeah, of course. Thank you. Of course, yeah. But then, so that's an important thing. It's a Gauss's law that when this integrated, that actually the right-hand side should be the total charge, but the total charge on internal space has to be 0, which forces us basically here on the right-hand side to insist that the sum over charges associated now with each of the cycles, homology cycles, have to add up to 0. So the actual fact that we are not allowed to have any charge escaping the internal space, that the total charge is 0, can be now rewritten, working with the left-hand side, as a statement that the charge is specified by cycles in internal space have to add up to 0. So this is really in the sense of homologies of the cycles. Okay. So another way, yes?
So you wrote the action for the 10D degree.
Yeah.
How come you don't have a 25 degree for the F1?
F1?
I mean, for the C1 field, which you were
Right, so I am basically writing it as by using duality, I'm writing this as H2, right? And then I can write back in terms of C1.
Yes, but so
Yeah.
in terms of C1, at the levels of Lagrange, then I have DH2, which star DH2. But then shouldn't I have a piece of term time and which is something that's like C1 with
I think I'm fine to deal just with the C7 per se, okay? It's fine to deal just with C7 per se and look at equations of motions associated with. Basically, if you view that as electric, C1 is then magnetic version. And so these 6 branes actually are magnetic versions of C1s, okay? So let me just, because these are sort of side things, but are rather crucial as far as constructing consistent models go, is that actually whatever set of branes we put on internal space, equations of motion force us, for this C7 gauge potential, force us that the sum of all the charges associated with this branes living on cycles have to add up to 0. So this is one key consistency condition. Sorry? No, this is now in the whole internal space, M6. And this, because those are closed sector forms, right? Yeah, I think you're right. But now equation, this is in the whole space. Well, but I wanted to use the Gauss's law. I somehow wanted to use the Gauss's law.
You're just saying this
In homology, yeah, I'm saying that from the equations of motion, but I wanted to use Gauss's law, and I write that I'm just, so using the Gauss's law, I just wanted to argue, that Gauss's law tells us that, the total charge, okay, in this internal space has to be 0. But it does. Yeah, it's obvious. It's obvious because this is the exact. So left-hand side is 0, and then once I do it in homology, okay? But so basically that's what I was doing. I was doing integral over this, okay? But now I'm anyway, as you said, the equation itself, even not going into. It's the form like that automatically ensures that because the left-hand side is exact.
The integration has to be essentially close with probably just integrate over each pi or something.
Yeah, piece by piece, okay? So it's actually, you're right. I mean, I was a bit sloppy. I'm sorry. I was a bit sloppy with that. So what you're saying is, what you raised that is this thing, right? It's really over each of the subs. I can go into the basis of 3 cycles and say that each of them separately, in natural basis of 3 cycles, that total charge associated with each of these 3 cycles adds up to 0, right? So that's, as you said, doing this integral now over the whole set of 3, a basis of 3 cycles is 0, and then as a consequence in homology, this is equivalent to that. Okay, so yeah.
Sorry, can we write that equation to some identity
Probably, yeah. But then those are the dual guys again, right? So let me just instead of dwelling on that, let me just focus on the property of this expression in homology, okay, which tells us that as a consequence, all the charges, okay, now in the homology of internal branes have to be 0. Okay, let's try to do that for the case of having a bunch of branes, but put them on the torus, because I did spend time describing, particular cycles wrapped on torus in terms of the basis of this A and B cycles. So I introduced this set of A and dual B cycles in terms of 1 cycles on each torus. So that was, for example, there were 4 of them here, A1, A2, A3, and then we have A1 with B2 with B3, and then we have 2 more perturbations. For A's and B's analogously, so that was a natural basis of 3 cycles that we build out of 1 cycles on each of 2 torus. So this was of the structure B1, B2, B3, and then we have B1, A2, A3, and then 2 more perturbations. Okay, and then the actual going back, right, in terms of writing each 1 cycle as N1, A1 plus B1, M1, so N1, A1 plus M1, B1 for 1 cycle cross like this. So this is straightforward to see that the corresponding integer numbers in front of each of these basis cycles would be here N1, N2, N3. This one would be N1, M2, M3, and you can see the picture, right? So basically, you see, this is our basis of cycles, and we can identify charge with each of these bases of cycles. So we can expand our set of branes, right, in terms, so each brane will be now expanded as a product of the cycles, and AI plus MI BI for each of the brane, and taking that as a product over all 3 tori. Okay, so this would be this in homology of those cycles. I'm describing arbitrary cycle on torus in terms like that. So condition like that, it reduces into explicit form in terms of this wrapping numbers N and M's. Okay, so let's say, so this now I'm the situation on torus. This condition would become now for each of these charges, okay, and would be of a form like that. NA, and 1A, and 2A, and 3A, summing over all of them being 0. Similarly, second one, NA, and 1A, M2A, M3A equals 0. So you can imagine how the story goes, okay? Now, if we stick to supersymmetric configurations, okay, if the cycles that branes wrap are such that they are supersymmetric, it will turn out that actually the total brane that wraps the sum of all the supersymmetric cycles has to have the net charge 0. Now, if the cycles were all supersymmetric, we are talking about a supersymmetric brane, total brane, that has net charge 0. But for supersymmetric brane, charge is tension. Okay. So basically, the answer would be that this is equivalent to having no brane. Okay. So basically, this global condition of not having any charge without doing something else, with just branes wrapping cycles, okay, for supersymmetric backgrounds could never be satisfied. And so in other words, for this simple case, the only conditions we can satisfy, okay, would be that all this NAs would end up being 0. Okay, so no branes at all. Okay, so this global condition is actually very constraining, right? And forces us to deal with the constructions on compact spaces that introduce orientifold planes. Okay.
So this conclusion is not dependent on choosing this particular Torus?
No, it doesn't. It doesn't. I just wrote it here because I thought, you could do it. But at the end, you'll see that if all those cycles are chosen so that they are supersymmetric, the only solution you will have would be for all NAs equals 0. And basically, it's BPS argument. It's a general argument that the sum of all these BPS branes, okay, has to have total charge 0. But that means that the tension of this net brane is also 0 because charge is tension. Okay.
What happens if the internal manifold has a non-compact branch?
I don't want to do that because then I would have some large extra dimension closed sector closed sector fields.
This is some complex story. It's just not considering this kind of condition.
It does not make sense to consider it because if you have non-compact direction, that becomes part of our world. Okay, so we would have, let's say, two extra non-compact dimensions. Well, as far as those branes go, yeah, they are localized, right? Let's say I'm going to make extra dimensions transverse to the branes, if I can, right, large. But then I would have closed sector fields that would freely propagate there. So there would be graviton, 6-dimensional graviton, say, that would freely propagate, and that wouldn't work. So we never really formally decompactify it as long as we do compactification.
So if you have some propagating mode to the non-compact direction in the internal manifolds, then
so then it's being non-compact, right, means being of infinite size, right? Yeah, it's just not, I can't. I think, are you thinking about Randall syndrome idea in this context, doing NDAs? No. Okay. Well, then your effective theory is higher dimensional, right? It's not describing 4-dimensional world as we want to see it. Okay, I cannot formally completely decompactify unless I play with the curvature in the space, right? So that in this context, I'm never considering that, okay? All right. So this is, yeah.
Correct me if I'm wrong, but if this equation that you've written on
Yeah.
If I engineer it cycle by cycle,
Yeah.
doesn't that automatically imply that all the NAs are 0?
It's actually it's sum over cycles, okay?
But now suppose I integrate over 1 pi a to the.
Yeah.
So it's a 3 form. So wouldn't that lead to?
Actually, you see what contributes to charge in internal space is sum. This is basically in homology. This is that, right? It's sum over charges over all the branes. Okay, you can't just separately because they add up to certain. All of them contribute internally, right?
Yeah, I think another way of saying that is the pi's are not necessarily they're not orthonormal.
Oh yeah.
Okay.
Yeah, but that in this concrete example, you see that this is the orthonormal basis of cycles, right? But general cycle is not, okay? So that's why I'm going back to orthonormal basis and identifies each of them separately, okay? All right, okay, anyway, there is also, so this is the global condition that we have to satisfy, but I just argue that for supersymmetric examples, it has no solution, okay? So it actually has no solution for supersymmetric branes. So we have to do something else. We have to introduce the O-planes. Yeah.
Since right now standard we didn't say supersymmetry right now, can we calculate the standard model directly from this construction? We have the matrix formula.
Yes, you can. That's a good point. So indeed. So if you don't insist on supersymmetry, you can satisfy these conditions, right? Right? Actually, you can get infinite number of models, and originally, 11, 12 years ago, the Madrid group constructed large classes of non-supersymmetric models like that. So as far as its supersymmetric construction goes, it's not possible, okay? But if you don't insist on supersymmetric construction, and you say, okay, it's nothing in principle wrong by starting with non-supersymmetric constructions, as long as you satisfy this Ramon-Ramon charge condition. Okay? But you do encounter at loop level what we call Navier-Schwarz tadpoles, and we are not protected from large loop corrections, that arise if string scale is large, right? So we don't have calculational control over effective theory. That's sort of my view, but it's nothing wrong in principle, okay? And actually, originally, a lot of models that look like standard models in the spirit that I just mentioned, multi-stack constructions, right? And so they were done basically on tori like that. So on tori like this, and then specifying the intersection number on tori, just the way we calculated yesterday, okay, for different multi-stack examples, and dealing with still had to ensure that all the choices of these wrapping numbers are such that this is satisfied. And frankly, there are infinite number of models per se that could do that. Okay, but they are strictly non-supersymmetric. Okay, so maybe before we go to supersymmetry, let me mention a few other consistency conditions that are actually some of them are consequences of that, and another one are actually a consequence of further expansion of this Wess-Zumino action. Okay, so before we turn to supersymmetry, okay, let's talk about further consistency conditions just briefly. So in particular, let me talk about non-abelian anomaly. Okay, so we have models now where we have branes wrapping multi stacks of brane wrapping cycles, and our symmetries. Recall our gauge symmetry was U and A, say, cross U and B, etc., depending on the cycles that we chose. So in particular now, you may worry if your models that does satisfy this core global condition, charge conservation of Ramon-Ramon charge interval space, has some problems with non-abelian anomalies in this effective theory. Okay. So non-abelian anomalies will be associated with, say, triangular diagrams in the effective theory, let's say with U and A of that type. Okay, so we would have gauge bosons, let's say SU and A, SU and A. So let me just take them all SU and A. So this is now the second. This is non-abelian anomaly. But you see, since we know the spectrum completely, we know that the spectrum what runs here in this anomaly calculation are actually massless fermions that are charged under these SUN symmetries, SUN asymmetry. But we also know that all the fields that are charged under NA are in bifundamental representation under other branes, depending how many times a brane intersects with others. Okay? So basically, this anomaly can be written, the left-hand side result of this anomaly calculation is that the number of fundamentals under A minus number of anti-fundamentals of A. So you have to actually, this anomaly is proportional to the difference of the number of fundamental fields and anti-fundamental fields, okay, under this SUN symmetry. Okay? And so what I want to claim is that actually this is always 0 as long as this core supersymmetric, a global condition is satisfied, tadpole cancellation is satisfied. Okay? Namely, the reason is the following. Since we know that the number of symmetric and antisymmetrics, okay, is related precisely to how many times this branes intersects with any other brane. Because at each intersection of this brane A with brane B, we get bifundamental fields. Okay? And how many of them we have under asymmetry? If the brane B has U and B symmetry, we have that many fundamental fields. Okay. So A and B, okay, this intersection number, this is, so I'm going to use that from now on. Intersection number is intersection between cycle A and cycle B, say. Okay. So when brane A intersects, say, with brane B, we get bifundamental fields. We have that many of these bifundamental fields. So when we count the number of fundamentals under A, we have that many times number of B because, okay? And we have to sum this over to get the whole net number of A's, okay? If this intersection number is negative, then this comes with minus sign, and this is subtraction here. So it's precisely, so this equation can be recast in geometric sense, just as this equation, okay? And now I want to argue that this condition automatically implies that the sum is 0, okay? So the way you see that, yes? So the way you see that non-abelian anomalies are really identically cancelled, it's using now this global condition. So what I'm going to do is I'm going to take this condition on the absence of Ramon-Ramon tadpoles and multiply that. So I'm going to write that. But I'm going to write a little bit different. I'm going to write it NB pi B equals 0, summing over all B's. Right? This is tadpole condition, right? And I'm going to multiply that by pi A from the left. Just doing, this is equation in holonomy. And so I'm doing now product of the cycles with those cycles. And this then automatically implies that NB, so for each A, I'm going to do that. So I'm taking specific A. So in holonomy, A times B is this intersection number AB, and this should be equal to 0. And you see this is the same as a global anomaly condition. So it's well-known fact that once you have satisfied Ramon-Ramon tadpole cancellation, okay, they are never non-abelian anomalies in the effective theory that you get from those constructions in 4 dimensions. Okay, and it's just automatic consequence of counting the states. Okay. Now, there are still more anomalies. How about mixed anomalies? And mixed anomalies turn out to be non-trivial. So mixed anomalies turn out to be non-trivial. So now what I would like to look at is, so mixed, so U1A cross, say, SU and B square anomaly. Okay, U1A. So the mixed anomaly itself, so let me do, if I have a gauge boson associated with A symmetry, and then looking at triangular diagrams that involve now non-abelian gauge bosons associated with SU and B, this anomaly can be recast again in terms of the content, matter content. We can rewrite that back as intersection numbers. So this is the same as number of A's, and then there is intersection number. So it's proportional. This term is proportional to intersection number of A with B. So let me just write this as AB up to signs and factors. Okay? So this anomaly turns out to be equal to just no sum. It's no sum. It's actually taking A and B, and it's in terms of matter representation, turns out to be rewritten back just in terms of this intersection number. Okay? And it's non-zero. I cannot use tadpole cancellation to do that, to say that this is zero. This is in general non-zero. Namely, this U1 is anomalous in this effective theory. Okay? But the full theory makes this anomaly disappear because we have to add contribution, okay, from Wezumino terms. Okay? So in particular, what turns out to be the case is that we have to add to these diagrams now contribution that comes from this action, Wezumino action. So it's not the tadpole term that we already use. We have to go to higher order expansion. So let me just expand the field strengths. And we see that basically Wezumino action at the next order will involve C5 forms wedged with a trace of A. So let this be associated with U and A. And then we have additional term, let's go higher, C3 wedged with a trace of FA, wedge FA. But let me just call now that as B's. And then this involves only a billion guy, and if I have n branes, that will give me NA here. So those are basically the next order expansion terms of this Ramon forms, okay? First in higher dimensional theory, but now I have to reduce that on the corresponding cycles to get now effective theory in 4 dimensions. So now in particular, so this is now summing over all those A's and summing over all those B's. And so effectively what we now get when we reduce theory on there's 5 forums, Ramon-Ramon 5 forums on cycles, we would get 2 forums, right? 5 forums reduced on cycles will produce for me 2 forums, okay? So those are antisymmetric fields in 4 dimensions, okay? And so I can write this so effectively as I do reduction, so 4-dimensional Wezumino action, the relevant parts in this anomaly cancellation come in 4-dimensional Wezumino action that we integrating C5s over pi A. Schematically, I'm going to write that as B2A. Okay, so it's some 2 forum that cares which cycle I have reduced it on. So this I'm just going to be schematic on that. And so what I have is I have a term that I get in 4 dimensions after I've done this integral to get a 2 forum. So I get B2 forum wedged with 4-dimensional gauge field in lower dimensions times NA. So this would be the first guy. And then similarly, if I now reduce these 3 forums, I get 4-dimensional fields that is a scalar. Because it's 3 forum on a 3 cycle, I would get 4-dimensional fields that is a scalar. So this would now look, so I have a term, first term, so integral of C3 over the 3-cycle B will give me scalar field, which I'm going to call, it's an axion, let me call it phi B. Okay, and so that would be another term that would look like phi B, and then trace FA wedge FB wedge FB. So the effective 4-dimensional action involves term B wedge F, and then some scalar field that involves F wedge F. Actually, turns out that in 4 dimensions, if you do that carefully, that B2 is dual. So if I take D of B2, dualize it, and multiply it by intersection number. So let me do the right, since I need only one of them. So let me do that. I'm going to use, so this is, I'm going to use this one. dBA is actually the same as dualizing d phi b, and then multiplying by AB. Duality is a little bit more involved once I go doing this integral on the right cycles that are Poincare dual to the cycles that I introduce capital A and B. Anyway, you take it on face value that actually four-dimensional two-form fields are related to the scalar fields through the duality of that type. Okay, and now we can use actually these terms to get the same structure as this diagram. Okay, so what I'm going to do is I'm going to take this term here that will involve, so from string theory, from Wezumino action, I have additional set of terms that involve now gauge boson BB, so I'll be really only schematic here, but the structure has to come right. So these are BB, two gauge fields. That will now involve coupling to phi B. Okay? And I'm going to exchange phi B, okay, through a tree-level diagram. But recall that phi B is actually dual to B2. So this duality will actually now involve d phi B star. So here in this, that I will relate to BA as I AB D star phi B on the left-hand side. So on the left-hand side, you see this is BB star coupling involving propagator of this scalar field. But the way I map it onto the two-form field is through this duality relationship, and that now couples me to the U1 gauge field, which is this B wedge F. Okay? So this is a three-level diagram that has precisely the structure times NA. Because B wedge F, okay, I'm going to write this B through duality relationship, but there is a term NA here as well. Okay? And so basically from the structure I see that this diagram is also proportional to NA and AB. Okay? Has precisely the same structure. The signs work, and it's precise cancellation of this mixed anomaly, okay, due to proper implementation of higher order Wezumino terms that are there for the effective D-brane action. Okay? So effective theory of our meta field looks like it has anomalous U1, but the full theory doesn't, because there are those terms that precisely cancel this anomaly. And this goes under the name, it was first found in the old days for heterotic string theory by Green and Schwartz. Now this is for D-branes, and I think the person who was doing that first early ahead of anyone else was Agnotti, so some people call it Green-Schwartz-Agnotti mechanism. Maybe it should be called also Polchinski-Gimon mechanism. Anyway, the point is that this is automatic. This is an important manifestation that actually the self-consistency of the theory really that comes from terms like that. Okay, so that was a side comment, really, but just telling you that things work. Okay, and the reason is I hope to use some of this stuff to do actually non-perturbative effects and calculating properties of actions coming from here. Last but not least is the observation that in the presence of terms that we encounter, which was next order expansion, okay, B wedge F, is that actually these terms are such that we get a mass for these U1 gauge bosons. Okay? So the way you can grammatically see that again, recall that B wedge F, because it can be made, so as a diagram itself, let's take A gauge boson. Using term like that, it would couple to D of B, which is dual to D of phi. right? So that would involve now, in principle, 5 fields, or let me say, so it would involve DBAs here. If I exchange them accordingly, and then couple back to DBAs, I would get effectively a term that would have gauge boson entering through exchange of these axion fields, okay, back into that, and that will give me effectively the term AA. Okay, so basically this term is responsible actually for giving masses to those U1s. So these U1s in theory of just charge matter are anomalous, and that's why we often call this guy anomalous U1s. Okay? But in full theory, there is no anomaly associated with these U1s because it's canceled by Green-Schwarz-Agnotti mechanism. Okay? But there are consequences that have to do with the fact that actually this U1 gauge boson is massive guy there, but the theory has precise U1 gauge invariance still in it, encoded, because, okay. So to get maybe back to this issue that Tom asked about, taking combinations of U1s, okay, and making them massless. Generically, each of the U1 of UN has coupling like this, okay? And you have to take combination where the natural, in the right basis of these axions, this coupling disappears. So there are additional conditions on ensuring that when we sum all that in the natural basis, what we call U1 of hypercharge has prefactor 0. So those are additional conditions, necessary conditions on having hypercharge massless. And you can ensure that. 1 per se, it's massless, is massive, each of separate U1s. But linear combination can come in such a form that they cancel precisely. Okay? Yeah?
There are no loop corrections to that diagram?
Sorry?
There are no loop corrections to that diagram?
To which one?
To the two-level diagram that cancels 0?
No. This is actually, as cancellation goes, you can actually show explicitly that this chiral anomaly that can appear, okay, because of U1 behaving in a certain way is precisely canceled by terms like that exactly in the whole action. At the diagram level, it comes like this. And it's only tree level. Okay? All right. So those are sort of some side comments associated really with certain consistency of the theory. I still have 5 minutes, okay? So as I said, and as you pointed out, is that actually, in principle, we can be now dealing with construction of models that are free of anomalies as long as the tadpole cancellation is satisfied, okay? And none of these issues are really issues. The theory is self-consistent, okay? But the only way to get models like that is not to be consistent with supersymmetry, okay?
So for non-supersymmetry, are massless formulas protected from loop correction?
For supersymmetric theory?
No, for non-supersymmetric.
No, so what I said is you can now construct effective theory that is non-supersymmetric, satisfying the tadpoles, which you can, okay? But what you would have, your spectrum is not supersymmetric, right? So you don't have protections.
So massless formulas are not protected.
Massless?
Yes.
Chiral formulae are protected, okay? But masses of scalars or and actually further higher order corrections, we would introduce order by order big corrections coming from Neveu-Schwarz scalar fields like dilaton, which comes from the metric part of, right? So they're order by order big corrections there. Okay, so we don't have protection mechanism, right? And all these corrections will be at higher order of M string. So unless M string is TV, we really don't have, any reliable way of dealing with effective theory, except maybe for chirality and gauge symmetry. Okay? But other stuff, couplings and all that, and masses of scalars, all hell breaks loose there, right? So per se, as far as gauge symmetry and chirality goes, this is fine. But at the level of calculating any kind of couplings, then you're really in trouble. Okay. So that was primarily the reason why we turned to supersymmetric ones, because there you really have non-renormalization theories in your effective action. At least as far as superpotential goes, whatever you calculate will be true to all order in string loops at least. Okay, and but philosophy there is that at string scale you start with supersymmetric theory. You have control over string corrections. Okay, but then you're dealing now with this effective theory that you have to bring down to low energy. And as a consequence, you have to break supersymmetry, but now at lower energies in effective theory. String theory is forgotten at that point. Okay, and that's more of a philosophy in this context, because at least we have some control over some ideas how supersymmetry could be broken and how much we can trust the effective theory that we write in 4 dimensions. Okay? Yes?
Isn't it correct that if you choose one of these non-supersymmetric things, the flat space you started from is also not stable?
Indeed.
There are corrections.
Yeah, this is what I was referring, dilaton. Yeah, and this is this Susskind-Fischler mechanism, hoping something will balance. But it's order by order, it's huge, yeah.
The solutions, the thing that you get from Fischler-Susskind would be a singular solution of equations of motion. So you completely lose control.
Yeah, I think so, but maybe Eva Silverstein wouldn't agree with me. She likes non-supersymmetric ones. You see, in principle, it's nothing wrong with them. Okay? In principle, okay? You just don't have calculational techniques to handle it beyond certain point, right? Okay, you disagree, okay. Okay, anyway. All right, so maybe we should take a break. So what I want to do next is I want to deal with supersymmetric theory, and I have to then satisfy tadpoles by introducing now orientifold planes. And mention a few models, okay? And then we'll see how far, at least I'll start with some preliminaries about non-perturbative effects in this context, okay?
So
thank you.
Any triangle anomalies for your 4D low energy vector theory?